Hi everyone, and welcome to lecture 6 of Math 350. And today we're going to talk about sums and products in a deeper way than we've talked about so far. And we're going to talk a little bit about how Mathematica handles infinity. And then I'm going to show you a little trick for combining multiple plots together into a single plot at the very end. There will also be a graphics component to this week's material, but it will be covered in the separate supplemental notebook. And I might record a short supplemental video to go with that, but it's not going to be contained in here. So sum and product function in Mathematica are intended to recover the sigma and pi notation that we see in calculus classes. That is, we're going to take some sort of formula that defines a term or a set of terms, and then we're either going to add up a bunch of those terms together or we're going to multiply those terms together depending on an index set that we draw from. And so prior to this, we've mostly been working with plus and times, which are ways of generating an entire list of numbers and then applying that to it. With sum and product, we have the structure of applying plus already taken care of, and all we need to do is be able to write down what the formula for the terms should be. We'll start with a symbolic version of this, and then we'll talk more specifically about how you build a coefficient function. So this command that I've written right here, this sum, is the command that we're after. What sum does is it takes a formula that defines a term depending on some index I, and then it reads off of a list of indices, puts that number into the formula, and then produces the result by adding them all together. And so symbolically, what Mathematica thinks when you write this down is exactly what we've written. We haven't given it anything specific, so it thinks, okay, so you want me to take AI, you want me to plug I values in between 1 and k, and then add them all up. Well, the best I can do with that is this sigma notation. I have a notation for that. And likewise with a generic product with nothing defined, you can see here that, again, we have this unspecified formula AI. We're feeding I values between 1 and k into that product. And so what Mathematica does is it takes internally a list of numbers starting at A1 and ending at AK, which it knows it doesn't know, and then smashing them all together with a product. And so if you haven't seen it before, it's been a while, that's what that capital pi means, is product, in the same way that the sigma is a capital S, which stands for sum. Now, one of the reasons that we're working generically is because I want to show you something about how the index sets work for these. This came up in the homework for week 2, but a nice thing about the way that Mathematica works with these functions is you can put any set of numbers into the index set, and Mathematica will use that as the index set for whatever you're trying to do. So this command produces the number starting at 2 and ending at 10, counting by a step size of 2, so it's the even numbers between 2 and 10. And if you give it to Mathematica as a list of indices, it is very happy to take that list and stick it into the function AI, and so you get the symbolic sum A2, A4, A6, A8 plus A10. Likewise, in this product structure, suppose that you want something indexed by prime numbers. Well, this is what this would do. So we have a range of 4, so that's the numbers 1 to 4. We apply the prime command to that in a list way, so we're mapping it on, which means we get the first, second, third, and fourth prime, and then the product is actually using those numbers, the first, second, third, and fourth prime, as the index set for this product that is computing, which is why we get A2 times A3 times A5 times A7. So this is very flexible. And I'll point out that you can specify specific elements as well. If you don't want to use a command to create a list, you could do something like the sum of AI over an index set that looks something like, let's say, I gets pulled from the set 2, 10, and 400. And you can see that you're going to get A2 plus A10 plus A400, right? That you can choose not just runs of indices that go 1 by 1 or 2 by 2, but that you can be much more precise about choosing those. And that turns out to be a very useful feature when you're constructing more complicated sums and products. It's often the case that the most difficult thing about working with a sum or product function is not the index part, or in thinking about sigma notation or pi notation, it's getting a formula where you're not given the term in an explicit function, but instead you're given some sort of structure where you can read off what the function is supposed to be, but it's not actually a formula. And let me show you what I mean by that. So term functions, we can start with a really simple example. Before we move on to this one where I don't have a formula, let's work with one where we do. Let's suppose that we wanted to find the sum of 1 over n squared between n is equal to 1 and n is equal to 10. Well, I could define a term function ai is equal to 1 divided by I squared. And probably I should use a delayed assignation here so that I've actually function. So now that's a coefficient function. I could have used a pure function here as well, and frequently it's more convenient to do that. But for the purposes of what we're doing, let's suppose that we have ai, and we've defined it to be 1 over I squared. This is something that's easy to test because then you could put an a3 and check that you get 1/9 out the other side. Well, if you wanted to add those up between 1 and 10, then you would just use the command sum of the ai's starting at 1 and ending at 10. And Mathematica is going to do its best to give you the most precise answer, so it may be the case that you don't actually care about what the fraction is, you're just looking for a numerical approximation, and so we get something like that. It's more complicated when I have a problem where the term that I've been given, like this right here, is clearly a pattern, but it's not something that there's a clear function for. So we're trying to add this thing, but it's not stable in the sense that I can get the next one from the previous one by multiplying by a new fraction, but somehow I have to have a formula. If I want to use sum, I have to have a formula that I can plug a single number into and produces that large term with the numbers that are starting at 1 and being multiplied by 2 every time, and there's n of those. So if you were working with, say, n is equal to 3, there would be 3 numbers, 1, 3, and 5. If you were working with, on the bottom, you'd have the numbers 2, 5, and 7 as n was equal to 3. And every new iteration of n that you input, you're going to get one extra multiple on the top and the bottom. So the challenge in a problem like this, and the challenge on many of the hard homework questions on this week's assignment, come from taking formulas that look like this and figuring out how to write them as a function that you can put a number into and get the same thing out. So I want to walk you through how I would approach this problem to give you a basis for this, what can be kind of a complicated idea of reproducing complicated expressions. These things come up all the time, say in differential equations or in calculus when you're doing the series, because oftentimes we'll get these sums that have terms that are built themselves out of sums or out of products and that change as the index increases. So if I want to use Mathematica, the first thing I might think is, let me just see if I can figure out what the fourth term is. If I could produce the fourth term, then maybe I can make it from a function that I could turn into an anonymous function by replacing 4 with something else. So if I'm thinking that I want to be able to expand or contract this thing, the central object that I should be trying to construct out of is range, because range is something that can increase or decrease depending on some kind of input. So that's why I've chosen to build this out of range 4, because if I did the same thing to range 6, you can see that this thing is flexible. It can produce the list of the numbers that look exactly like the terms that I'm after by plugging in a simple number right here. Likewise, with the denominator of these fractions up here, I need to go 2, 5, 7 up to 3n minus 1. Well, if I take the function 3n minus 1 and apply it to range 4, I get 2, 5, 8, 11. If I apply it to range 8, again, I'm going to get a list of numbers that is exactly what I want. Oh, that's not quite right, is it? It's supposed to be 8. So, make my own problem consistent here. Thanks, Mathematica, for fixing it for me. Right, so I get the same list of numbers that I'm interested in. So if I put in 8 into 3n minus 1, I get 23, which is precisely what I want. So I've got the bits and pieces that I need now. What I need is to take this and turn it into something that produces this. So there's a couple of different approaches that we can take to putting these two lists together to produce the function that we want inside the sum. One of the more interesting ways to go, and the way I would think about this, would be instead of producing two different lists, let's just produce one list, which means I'm going to make a function that does both of these things at the same time. So I'm going to take 2n minus 1, and I'm going to divide it by 3n minus 1. And I'm going to take all of that, and I'm going to apply it to the range, say, of 8. And that should give me a list of all of these things divided. doesn't really matter what order I do it in as long as I've got all the pieces there, right? So what I see here is I've got the 1/2, the 3/5, the 5/8, and every fraction that I'm adding in line. So now how do I multiply them all together? Well, I could do this at the end, or I could do it inside this function so I can just apply it once. So now that I've got this, I might think, all right, the next step here is going to be to take that list of numbers and turn it into a product. So maybe what I can do is to change heads. So I'm going to take times, and suppose I naively just apply times to this thing. Well, I get this list that doesn't look like it did anything. And so the question is, why? What happened here? The answer is, whenever you're doing a head change on a function like this, you can think to yourself that Mathematica likes to change heads on the very first object it sees that it can change heads on. So give it the compound object, surround it in parentheses, and then times will apply at the head change to times will apply after all of that interior operation is done. Okay, so if you get a result out that you don't expect, or your code doesn't seem like it's working correctly, and you've done something that involves changing heads on a list, surround the object that you're working with parentheses. Okay, so let's actually check and see if we believe this. If I go back up to this original pattern here, if I put in 1, I should get out 1/2. So let's check and make sure that that happens. Okay, that's great. What happens if we put in 2? Well, we should get 1 times 3 on top and 2 times 5 on bottom, which should be 3/10. So if I put in 2, I get 3/10. Okay, so now I buy that this thing is a function that will produce the coefficients that I'm after. So even at this point right here, I don't have to name this function. If I want to do this, if I would like to take this thing right here and I want it to produce the sum from 1 to 10, I could anonymize this function, function n of all this stuff, and then I could feed it into the sum function. So I could take the sum of all this and run it from n goes from 1 to 10. And so there we go. There's the answer, right? This is the sort of situation, though, where for a lot of people, it's going to be easier to understand what's happening if instead of writing this up as some sort of fancified one-liner, which we've done right here, where you sit down and look at it and it's not even clear what's happening inside. For a reader, or for someone who's developing this from scratch, if you want to be more natural about the way we actually did this problem, what we did was we noticed that at this point right here, if I took this thing and I applied times to it as a new head, and then what I did was I took this 8 and I used it as a variable so that it could expand or contract depending on which term I was at. You could actually just call this something like bn. And now you just have a function that's actually very easy to read. And that function here, this function, is actually the same function that this is inside here. But notice that when you actually compute the sum now, you're going to get the sum of the function bn evaluated from n goes to 1 to 10. And now you get the same answer, but it's obvious what you're doing here because this is the term. So you define the function for the term, and then you sum that term right here. So you define the bn, you take the sum, you get the same thing. So this line and these two lines together, this is the same operation, but two different approaches. One, a named function approach, which has its advantages, and one, an anonymous function approach, which also has advantages. If you're not asked one way or another to use pure functions or named functions, you can use the way that you think is easier to debug and the way that's easier to read. So that's completely up to you. So now let's move on and talk a little bit about how Mathematica handles infinity, because after all, infinite sums are a sort of very common object to want to analyze in mathematics. So Mathematica is reasonably good at handling objects involving infinity. And there's two ways to create the infinity symbol. We talked a little bit about this last time. You can type slash square bracket capital infinity, which is the symbol. And I hit tab halfway, so let me actually slow that down again. Capital infinity close bracket. And as soon as you close the bracket, Mathematica is going to put the infinity symbol in there. And unlike LaTeX, it's actually a mathematically meaningful object in Mathematica. So for example, if you have a limit that you want to ask about in Mathematica, you can do that. So if you had the limit of 1 over x as x goes to infinity, Mathematica will tell you that that limit is 0. And we can use infinity in the same exact way when we're talking about sums as well. So rather famously, the sum of the reciprocals of the squares is equal to pi squared over 6. Whether it's being done algorithmically or because Mathematica has been hand programmed to produce this result, you can compute the same exact thing in Mathematica using the sum command. So the sum of 1 over n squared as n runs from 1 to infinity is pi squared over 6. If you start putting different values into this, for example, here we've got the sum of the cube, 1 over the cubes, it's going to give you something called the zeta function. And the zeta function is actually the function that recovers these things. It's the function that when you put in positive integers produces the p series. So that's what we're working with here. If you remember from calculus that 1 over n to the p is called the p series, and they converge when p is greater than 1. And for values where p is positive, you're recovering what's called the zeta function, right? The zeta function is a function that kind of captures that into one object. Okay, just to point out again, more complicated limits here. This is a very famous exercise that you usually do when you're taking calculus and you learn L'Hopital's rule, is to show that this definition of the number e holds. So 1 plus 1 over n to the n as n goes to infinity is e. So it's comforting to know that Mathematica knows that. Sometimes if you're trying to do asymptotic explorations, it's not always the case that infinity is going to be what you want. So if you actually want to be more precise about looking at asymptotic behavior and asymptotic approach, you can construct alternative explorations to this by using the manipulate command, is one way to do it. So for example, if you set up a manipulate environment around the sum, say, of the alternating harmonic series, that's -1, +1/2, -1/3, +1/4, and so on, and you compute this, where you manipulate over the number of terms in the sum, you can actually see this series converge. So it converges. I mean, the reason that we believe it converges here is because it's stabilizing, right? By stabilizing, I mean, as n goes on, I can see that what's happening is the digit that's moving in this decimal approximation shifts further and further and further out to the right as it goes. And that is exactly what we expect to see in a series that's converging. Of course, that's not a proof that it converges. It's just evidence that it does. I'll point out here that you can also use plots to explore asymptotes. So the sum of the reciprocal squares we already showed was equal to pi squared over 6. This is what I wanted to show you about, like a sort of trick you can use if you want to combine plots together. You can actually name variables for plots that you create. So what I've done here is I've made a table where the first element of the table is the number of terms in the sequence. And the second entry in the table is the value of the sum from 1 to n of 1 over k squared. In fact, actually, let's just take a look at that real quick and see what it looks like. So you can see it's a bunch of coordinate points where this was the upper index of the sum, and this is what that sum added up to. So if you want to store a plot of that, the first thing that you might actually want to know is, how do you plot a list of points? It turns out to be sort of amusingly irritating to try to do that with the plot function. So Mathematica has a function called list plot that is happy to take in x and y coordinates and produce a scatter plot of that for you. So you might ask, well, why am I doing this? Why do I have a plot where I've stored it in a variable name and then I suppressed the output? Well, because I want to make two plots. One plot that shows this sort of asymptotic growth of the partial sums of this series, and a second that shows the asymptote that I already know is true for this series. So in this case, pi squared over 6. And so I've also made that into a red plot. And then if you use the command show, if you feed the show command multiple plots, what it does is it puts them on the same set of axes, which is very, very useful thing to be able to do. So show is very good for that. And so you can see that's what I've done here, is I've taken this asymptote that I suspect is true, and I've plotted against this sequence of partial sums as the n values, the upper index, got larger and larger and larger. And this is pretty strong evidence to me that I've got the limit of what I think the series is correct, because if the partial sums are asymptotically approaching what I think of as the infinite series, that's what it means for an infinite series to converge. So just to illustrate here, what does it look like if a series doesn't converge? Well, let's construct the harmonic sum. So that's 1 over n, or 1 over k, where k runs from 1 to n. And here, if we use list plot, you can see that it doesn't actually look like it ever slows down. It just grows and grows and grows. And if you don't believe me, just take a larger plot. It could be a minute while this evaluates here. Let's see. Okay, so you can see that now when I've plotted from 1 to 400, I was plotting to 6. Now I've put 4,000 terms in, and the sum has grown all the way up to, above 8, and the shape of the graph hasn't changed. It's continuing to increase, sort of, it looks like logarithmically. And that's actually the behavior that it has. It's like a log x type behavior. So what's happening here is that this sum diverges. There's never curls over, so it's flat. So it's a useful thing when you're doing this kind of analyses, to be able not only to rely on Mathematica to do an evaluation at infinity for you, but to be able to use tricks like this where you can do asymptotic evaluations with your own manipulation of the numbers. Now, I want to reiterate again that this is not a proof that any of this stuff is actually true. This is all heuristic evidence for the divergence of the harmonic series or the convergence of the reciprocal of the squares. But in mathematics or engineering or physics or computer science, if you have a problem that you don't understand asymptotically, it's better to start with evidence of what you think is going to happen and then work towards that answer, rather than starting blind and having no idea where to proceed. So today, in this short lecture, we covered sum and product. We covered a little bit about term functions, both pure and named. We talked about infinity, and we also talked about general approaches to asymptotics. And we talked about the show command, which is used to collect multiple plots into the same figure. Okay, so that's enough to finish most of the homework problems. The graphics notebook is the supplemental notebook this week. I don't have a specific video for that made yet. If there's demand for one, I will certainly be happy to go into some of the particulars of the graphics function, but that's one I encourage you to get in and get your hands dirty on your own to start with. And good luck. I'll see you in Slack this week. Take care.